Okay, from the lab, you're going to get two graphs. You're going to have one graph that's speed versus radius, and one graph that's speed versus force. Both of these graphs should end up being curved, and they should be curved like that. And so from these graphs, we can see that speed is proportional, speed squared is proportional to r, and that speed squared is proportional to f. If we combine these two together, then we can say that v speed squared equals f times r, and that f equals speed squared over r. If we're trying to relate this back to acceleration, which we now are going to call centripetal acceleration, which is the acceleration of something moving in a circle with a constant speed, then we know that F has to equal mac. And so what we end up finding out is that the net force of something moving in a circle equals mass times speed squared over r, where this term right here is the centripetal acceleration. So we can also add to our toolbox that AC equals v squared over r. And so we can see that the more the speed we have going through a turn means we're going to have more acceleration. And the smaller our turn is, the more acceleration we're going to have. So speed squared is proportional to acceleration, and radius is inversely proportional to acceleration. And so how does it relate to us in terms of forces and motion? And so nothing much is going to change now, except instead of saying just that F equals ma, and we're undergoing uniform and a changing direction. And so that's when we would use then. Once this happens, we'll say the sum of the forces equals mass times AC. So now what are we going to do with this? So let's just look simply at the example of the lab we did. So here's the rubber stopper setup that we had, of force coming down here. Masses. And so let's say we wanted to determine what is the, if we know what the force is, let's say the force is 20 newtons. We know the stopper has a mass of 0.05 kilograms, and this string has a radius of 0.20 meters. What is the speed of the stopper going to be? So our force diagram for the stopper would just be that there's a tension force going in. And so then we can say this, we can say that the sum of the forces equals the force of tension in the direction of acceleration. There's some vertical stuff going on here, but we don't really care about that because it's not accelerating vertically, it's only accelerating horizontally. So we can say the sum of the force equals Ft equals m times a, but since this stopper now is undergoing uniform circular motion, I put a little c after the a, so it's centripetal acceleration. So I can say Ft equals mv squared over r. So I can say 20 newtons equals 0.05 kilograms times the speed squared divided by 0.20 meters, and then you would solve for the speed. Say we had a scenario where we had something moving in a vertical. Let's say I had a yo-yo. So here's me. Say I'm spinning a yo-yo in a circle at a constant speed, and I want to find out what is, let's say, what is the maximum tension, or what's the tension in this string when the yo-yo is at the bottom of the circle. So if I draw a force diagram at the bottom of the circle, I'd have a tension force pulling up and a gravitational force pulling down. Now we said that when something's moving in a circle, it has a centripetal acceleration, and that centripetal acceleration always points towards the center of the circle. So in this diagram here, I know that tension force has to be greater than the force of gravity. That also makes sense because the yo-yo was traveling down, and after the bottom of the circle is going to travel up, which means there has to be more force pulling it up than pulling it down. So then I'm just going to do what I always do and make a net force equation, say sum of the forces now in the y direction equals Ft minus G equals MA. But now things moving in a circle, so I say AC. And so I can say then FT minus, let's say the yo-yo has a mass of 0.5 kilograms. Let's say the circle has a radius of 0.25 meters, and it's traveling at a speed of 5 meters per second. So I can say that, I can finish my equation then, I can say that this equals 0.5 kilograms times 9.881 newtons per kilogram equals 0.5 kilograms. Put the v squared over r in for the AC, so I say 5 meters per second squared divided by the 0.25 meters, and then you would solve for FT and make sure that your FT comes out bigger than the force of gravity. Remember, there will be some questions where we're just going to tell you the time for one revolution, say maybe is 5 seconds, and that the radius is, say, maybe 0.8 meters, and you're going to have to, in some cases, compute the speed prior to then plugging it into the v squared over r in order to find the centripetal acceleration. And that should give you a good start on the problems you're going to look at the worksheet tonight.